Okay, for people who are joining this live stream, we're going to be talking about calculus and algebra functionality for the next version of Wolfram Language. And let's get started. Okay, so the big picture is 11.3 was the land of asymptotics. So what's next for the next version?
So the headliner is still asymptotics, and these are, so in that time we had solvers for integrate and differential equations. Now it's sums and difference equations, as well as algebraic equations.
Okay. I don't understand what asymptotics solved. I'm about to find this out, I guess.
Right.
So these are, okay. All right. So where should we look? Shall I look at examples here? What's the...
It's not there. So you go to the page. For those guys, I meant to put in a few key ones here, but if you go to the reference page, it's full of examples for each of these.
Okay. Should I be in version 12 in the
11.3? I mean, sir, 12 X kernel if you want to run it.
Okay. All right. My head branch build seems to have turned white. I don't know why. It's odd. And a little suspicious. What's that?
Seems pretty white too.
Okay. Okay, so we start off with asymptotic sum. Okay. I think I need to look at some examples here. Okay, so this is saying, by the way, this is, somebody should report, is there somebody from project management or otherwise here? Or not? Because there's a bug here. This is a bug for John. This is the new 64-bit front end, I think.
I'm sorry, what's the bug? I can report it to him, but I don't know this specific...
Oh, the magnification pop-up is missing.
It's not missing, it's moved. If you look at the top right corner. That's still under discussion, but what its final...
resting places. Well, what's that weird white area down there?
That's showing that there's something wide, right? So that should be a scroll, right? That should be a vertical scroll. It's not?
It's not. It's not that.
All right.
I think it's a scar from the sizing.
Okay. There you go. Oh, it's the scroll bar isn't taking up the whole.
The scroll bar appears to be useless. The scroll bar appears to be...
All right, I'll report this to the appropriate people.
Okay. Okay, so let's take a look at this asymptotic sum.
So the sum that's 1 over square roots up to n, and then you let n go to infinity, and you want to see how it scales at, when n goes large.
So, I mean, let me just understand this at a naive level. I mean, so if I were just doing this... Oh, boy, this is kind of confusing. I don't mind it at the top here. By the way, we've got a bunch of background noise here. So if I just say sum of this.
Like so.
I'm going to get some random harmonic number. Okay. And if I were to say series of that.
At infinity, it better be the same.
Okay, so why is there a single function that does this? Actually, it's not quite the same. It's actually not the same. It's notably not the same. I mean, it's got... Why is the powers... I mean, those are small as n goes to infinity. That's humongous as n goes to infinity. So this ordering...
Yeah, so... Right, okay. So series data does not have the ability to represent everything we need to represent. Now, it's a big project, and this is part of working out what the future of that should be. And so there are two aspects to it. One is, let's say in the univariate case, you need to have other kinds of scales to be representable.
Yeah.
Okay, and it's a careful trade-off. If we go too general, you can't do anything with it, but you can represent everything.
Sure.
If we go too narrow, we can do a bunch of things with it, but it can't represent many things.
Right, but is this an ordinary expression? Here?
It's an ordinary expression right now. And so the ordering that you see there comes from plus.
Yeah, I understand.
Okay.
Okay. Yep.
It's an experimental functions, Stephen.
Okay.
And so those are things that we expect to do there. The other thing, so this is about generating a bunch of these series.
But so for example,
we've also
asymptotic integrate doesn't do that. Asymptotic integrate produces something different, correct?
No, it does exactly like this.
Oh.
Because we can't use series data. This is what I'm saying. So we will want a container, but we want to carefully design that container. It just so happens that these scales earlier on here are simple enough that the sum order is what you expect it to be.
Okay. But so what's the difference between series of sum and asymptotic sum?
It is a whole variety of methods that will, first of all, series of sum doesn't do anything.
Do anything. It did something just fine here.
No.
Well, the sum evaluated.
The sum evaluated.
Oh, I see. I see.
So this works even when you can't evaluate it into closed form. That's the whole point of these things.
Yeah, I understand. But presumably you should make series of sum eventually work.
Right. That's for our next release. We'll have a whole slew of things to discuss there.
Okay. That's cool. By the way, we have this meeting coming up on generated parameters.
Mm-hmm.
Because that needs to be globally. What are you doing for generated parameters here? What are they? What are the parameters?
Well, this is the existing C, right? You name the parameters and it index them.
Okay. All right. Okay, fine. What does none do here? It just, what does it do?
So for an indefinite integral, it will not generate the general solution with a parameter.
Well, indefinite sum in this case, but yes.
Do you know what I'm saying, Stephen? Like for current integrate doesn't generate the C.
I see. I get it. It's because there's a constant integration type thing.
Yes.
I thought these were necessary internal parameters for some sub-sum that it was doing or something.
No.
Okay. So what is that? So that's an indefinite sum there.
Yes.
Fair enough. Okay. This is all quite magnificent. I mean, series of difference delta. So difference delta of this thing should return the original expression.
If you do an indefinite sum, the very definition of that is like for indefinite integral, that if you take the derivative...
Yeah, I get it. Yeah. It should give back the original thing up to constants.
Yes. Actually, no, there's no constant. The constant goes away for when you do derivative.
Well, this looks nice. I mean, I get it, what this is doing, I think. Asymptotic R solve value. Let's take a look at that guy. Yeah, this is a bug, this stupid white thing down here. But I must say that I don't object to that being up there, as long as I can find it. Yeah. So
there are two cases here. One is so that case, when you want to see how it evolves for large time or high index value, asymptotic series for that. The other case, just the example below, is when you have a parameter in there. That's usually called perturbation.
Which we already had for the case of differential equations. Asymptotic.
Right. So this one follows that pattern, right? Doing both.
Nice. Fair enough. I have no objections. Asymptotic solve. It's going to deal with things which were going to be degenerate, among other things, but as you increase, what is all of this?
It says you can approach the point at which you want the expansion from different directions.
So direction was an option for limit.
Yes.
A little bit general for that, but whatever. What's the difference between the y and the x here, really?
You view this as a function of x. See what I'm saying? Y is a function of x. If you look
I see. But why do you have to give the 0 there?
Well, you shouldn't. But that homes. But you can have multiple ones. No,
but in ordinary solve, there's no way you can say variable comma 0. It doesn't mean anything.
Right, but you're sort of right. I think
the second example, Stephen, doesn't have that, and then you get four different solutions.
Right. So these are solutions that approach a given point and all solutions.
So I mean, I would have expected that I would just do this, and it works fine. Yeah, I wouldn't put a brace in there. Why would you say a brace in there? So if I were to put, if I were to do this,
right, this particular one doesn't have any at 0. So if you do minus I, you'll get the first one.
I see. But if I were to do this, if I were to say solve, x squared plus x squared equals x. It's a bad example. X squared equals 1, x around minus 1. That doesn't mean anything, does it? No.
No.
So I don't understand this. I mean, it's an interesting syntax.
You have one, maybe if you go to the applications examples.
No, but I'm trying to understand, why didn't this work? I mean, that would be an interesting way to do it, is to say, go ahead.
Well, the point is that you are, basically finding the solution as a function of a variable, right? And so you're saying, what's your starting point, right? Here, x is the independent variable, just like in your asymptotic solve, x is the independent variable.
Yeah, but
the y is.
Look, I mean, what you're doing is you're saying this, and then you're expanding with respect to a, basically. This is the independent variable, the genuine independent variable for the solution.
No, that's the dependent variable.
Yeah, it's the dependent.
Look, y goes to x is your solution.
Yeah, but just like I'm okay. Sorry, you're saying independent. I'm getting that wrong. And honestly, this would be clearer if this was written out as this would be less confusing to me if this was written out here with this y being an x, right, and then this x being some kind of epsilon or something.
Sure.
And I would strongly encourage doing that in the
examples, you mean?
Yeah, in the example.
Well, I don't think that's quite right.
In the case where epsilon goes to infinity, it would look not that.
Obviously, you don't want to say for the case epsilon to infinity. You don't want to say epsilon, but
right. But I also think, right. I mean, you're talking about moving the right. You have some implicitly defined function, and you're finding the expansion of that implicitly defined function is what you're really doing. And being able to specify is which branch you're on is the
point. Yeah, I get it exactly. But I'm saying to you, and the reason that it doesn't make sense for solve is because in this case you're saying it's approximately 0, right? But in solve, it's zero when, I assume you mean it's zero when epsilon equals 0. Is that right?
Yes.
Correct.
Okay. So you're giving the case, whereas here, it would be meaningless to say something there because you either nail the value or you don't.
Right. Right. So basically, you have a solution of this constant equation, and then you are varying the parameter around this solution.
Right, but so in the case where if I didn't give a starting value there, then I'm going to get all branches, all whatevers, if you can generate it for me, right?
Yes, yes, and you will get into trouble if there are infinitely many.
Well, let's see what it does. Is this a case where there are infinitely many? Yeah, what did it
Probably.
do? So what's it doing here?
Well, it checks that it's not a polynomial, and there are infinitely many solutions, and it goes into trouble.
Well, we should say something there rather than just mutely saying forget it. It should say it can't solve it. I mean, rather than just I think in that case. But the basic point you're making here is the reason this isn't relevant for solve. So for what functions is it relevant? It must be relevant whenever there's an asymptotic thing going on, because why isn't it relevant to asymptotic desolve, for example, or is it?
Well, I guess it's in some future state when we have more DIEs, because then you get the algebraic equations in there as well.
Yes.
But really, even for asymptotic desolve and rsolve and so on, we localize. We say at what point the independent variable should be at. And in the cases that we can now solve, there isn't multiple solutions. Do you know what I'm saying? It's not implicit enough.
Yeah.
Right, and I think for desolve, it's like a boundary conditions, right? So y of we can say that y of 0 equals 7 or something. So that's we just put it in somewhat different place.
Well, let's talk about where it should be put here, because this is like in some of our fine minimum type functions. This is sort of a starting value, but it's a little different here.
Yeah, it's different. It truly is localized to that point.
Yes.
What do you mean by localized to that point?
Anything asymptotics is localized to the point at which you develop it around. Do you know what I'm saying?
I see. So this is developing around the point epsilon equals 0 and around the point x equals 0.
That's correct.
But you're automatically finding the possible points to develop around in a case like this.
That's right. But as Adam said, it's a problem when there are infinitely many, because our list don't take infinitely many elements yet.
There was a person at the summer school this year who did a very interesting project on infinite lists, which hopefully will get presented to you soon.
Okay.
Quite reasonable stuff.
Right. Yeah, Stephen, if you scroll down to the applications example, the first set, actually written out set of applications examples, then I think there's an illustration that makes this somewhat clearer. Yeah, and I'm not using the 0 syntax here.
Okay, I just want to know what's an analogy for that 0 syntax. In other words, selecting a solution around blah, blah, blah. Because it's not quite an expansion point. This is the expansion point here.
Well, no, really 0, 0 is the expansion point.
Well, but it's valid for all x. For small epsilon, but for all x.
No, right?
We're only getting branches of x that tend to 0, where epsilon goes to 0.
Yeah. How do you describe this?
Right. I mean, I suppose the alternative would be to add, support for specifying initial condition-like things, right? Where you would say, right, epsilon of 0 equals 0.
But what the heck is epsilon of 0?
X of 0, actually, but in this case, right?
Well, in the case that I was looking at his x and epsilon example, right?
Right, so it's x of 0. X is the function, epsilon is the independent variable, right?
Oh, yes, yes,
By the
yes.
way, I think this is super confusing, calling these y and x. I think it's a big mistake. I think you should come up with another parameter name for the expansion here. Because x is too often what you're solving for.
But you know, but yes, but what you're solving for is y of x, right? You're not solving either for y or for x. You're solving for y of x. That's the point. This is sort of returning to you functions.
No, I get it. But I'm saying you're solving for, look at the thing that's on this right-hand side here. It's that variable there. That's the thing you're solving for as a function of this variable here.
Mm-hmm. Right.
Okay, so what do you think is a good generic expansion variable? Epsilon probably doesn't cut it because of the infinity case. And I think these should be called, this should be x and x0 probably here. And whatever that parameter is called, I don't know what you want to call that.
Is t better?
Perhaps. What's that?
T.
A little bit. I would prefer something different because it's not a parameter like that. It might be e, for example. And then E0 and then N. So this is not what you want to say here. It's not y of x. Look, there's no y of x here.
Well, that's because you've replaced. Well, but you could have, right?
Could I have done that? I could have written it out like that, but you're not writing it out like that.
But that's what it's returning. This is what it's solving for. It's not solving for x. It's right. X is your dependent variable here.
But right? No. In this case here, it's solving for x.
Stephen, I was thinking that it's a little weird, but it might help you. So dsolve, when you specify for dsolve that you want to solve for y bracket x,
yes,
comma x. What it returns is y bracket of x, rule, and a solution.
Indeed.
Okay. Then we have another syntax we support, and it reports a pure function because it behaves better on the back substitution.
Yep.
Okay. And,
by the way, that's a baguette. If somebody can report it, that those two things are smooshed there.
Yeah, that's a known issue, I think.
Okay. But for dsolve, it really occurs like that. Y of x is really y of x.
I know, absolutely. Right? That's the point I'm making. Yeah.
Right. But it isn't ever occurring like that. But you are affected. The result. If you look at that formula that comes out in that very first example, it's exactly what we had there. It's just not saying x of epsilon.
But you don't need to. I mean, there's just like when we do, you could say y of x in the case of an ordinary solve. You could solve, say. I mean, I don't understand. We don't give the implicit dependence on parameters normally. The dependence on parameters is not in the x. It is in the x does not depend on the parameter epsilon. Epsilon is merely the solution that depends on the parameter epsilon.
So implicitly, x actually depends on epsilon. If it's going to satisfy that equation, x actually depends on epsilon.
Sure. As you change epsilon, you change the solution for x.
Yeah, exactly.
Right.
And that's what we report.
I understand, but I'm saying look, what I strongly suggest here is I think everything works. All you do is you say x, comma, x0, except I would first of all do the case with x here without discussing x0. I would first say it computes asymptotic approximations to solutions for x as a function of e to order whatever.
Fine, we can change that.
Okay, so now this one, so actually this is a weird case because this is sort of almost the transpose of what I would expect.
Right.
Okay, what does a multivariate series look like there? What does a usual multivariate series about, when I do multivariate series about a point, blah, 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 to...
So
whatever.
these guys, we can report today, our technology allows us to have up to multivariate Puso series.
Yeah. I'm sorry, for series, you're saying?
No, for this guy.
Okay, but if I say series of something like, e to the minus x squared plus y squared, and then I say, how do I do this? So do I say...
You do them one after another because it's fundamentally univariate.
Yeah, it's not. It
doesn't work.
It's going to give nested univariate series, which is not the same thing.
It doesn't work like that, Stephen.
Okay, but do you intend it one day to work like that?
Yes, probably, but it requires more investigation.
Okay.
For power series and simple series, that works out just fine. But we need to go beyond that, or we won't have anything very useful.
So that's a horrible mess.
Yeah. I mean, it's not wrong, but it's not the most useful.
Right.
And this is a very good case. This is like a power series, about as simple as things get.
No, I understand that. But so what does this now return? In the case where so this is returning an ordinary expression, not a series expression, right?
Right.
Yeah. Go down into the scope examples, and there is a section for that.
Okay. All right, fine. Let me understand this asymptotic solve. So this is saying, I see, this is restricting to reals, which is something you don't need to do for any of these other ones yet.
Right.
My God, that's exotic. Polynomial equation with Hardy field coefficients. That's getting pretty exotic there.
Well, yeah.
That's pretty wild. Is that what we do also for the limit case?
All six limit functions and probably some of the other asymptotic guys. Yeah, all the asymptotic relations also do this, since they're defined in terms of upper limits and lower limits.
Sorry. I spaced for a second. I got distracted by something. Could you repeat that, please?
So all six of the limit functions, right? Because we have limit, max limit, min limit, and then we have three discrete versions. Then we also have the six asymptotic relations, which are defined in terms of max limits and min limits. So all of those uniformly take this direction option.
With the same values for it?
Yep.
Okay. And with the same, this multi-directional thing is new for this, isn't it?
Nope, it's in limit.
Oh, okay, because limit also, okay, so let me understand the limit syntax, okay? So the limit syntax looks like what? The limit syntax is not this syntax, right? Is that correct?
Yeah, it's x goes to something, or vector x goes to something.
Okay, so this would be x, y goes to 0, 0, for example.
Right.
Okay.
Right, and then you could say, right, if you wanted to come from like the top right the first quadrant,
yeah,
right, you could say from above for both of them.
So you'd say then direction arrow. I see. For each one, it would be say from above, for example.
Right.
Fine. Okay.
So that means use from above for all of them, and you can independently specify for each variable if you want.
So let me understand this again. Okay. Yeah. So what happens in find minimum and things where you have multivariate? What does that do? Does it look like this again?
Syntax?
Yeah.
So there are yes, but you can do, because of history, there is a sort of a sequence of iterators or initial value specs, as well as the vector versions of it.
Okay. Okay. So there's a transposed version of this as well.
Right.
Okay. But are we recommending this version?
What I want to do for 12.1, but we need more investigation, is to switch into an arrow syntax that's closer to limit and make the order be, it'd be an option.
Okay.
But that's why they should remain experimental, because we need to change.
Which order piece? The N here?
Yes, I want that to be an option.
Why?
Because most important thing is to get the first term, and then you optionally ask for more.
I see. Fair enough. Not sure it should be an option, but maybe another option.
It's very useful for a bunch of other things for us too going forward, because what we don't want is asymptotic Laplace transform, asymptotic inverse Laplace transform, asymptotic Fourier transform, asymptotic inverse Fourier transform. There's going to be a lot of them. So there's like 50 more functions then. But we want a wrapper that makes all of these.
Well, so how would that wrapper work?
Kind of like series. It's like a future series, just about.
But so you're then proposing that solve would have an asymptotic wrapper, or what?
These key ones will have their own asymptotic, like these ones. But for these like integral and summation transforms, the primary way is that they should work by this wrapper. Just kind of like you wrap n around things. But we won't have the asymptotic Laplace transform explicitly available. Do you know what I'm saying?
Yes.
That's the basic idea.
So in other words, if a Laplace transform just evaluates, be happy. But
Yes.
if it doesn't evaluate, then you can try and get an asymptotic evaluation, just like you can get a numerical evaluation.
Right, where you make it inactive and you can still run through the asymptotic.
Right. Although we've ended up with things like n integrate and so on, and n sum. I guess your claim is that we end up with n integrate n sum, but we don't have n Laplace transform.
Yeah, exactly. And we're following the same thing here. So we have n solve, we have n sum, and we have n integrate and n desolve and so on.
Yeah, right. Okay, makes sense to me. I mean, and this implicitly implies that for things like Laplace transform, it's not going to be the case that it spends an hour trying to do do some symbolic form and then fails. It's going to be a fail fast type situation. Is that true?
Right.
Okay. But integrate is not a fail fast situation, is it?
Asymptotic integrate?
No, integrate itself.
No.
So
I mean, it should be, but it has a long history, so it's maybe.
I don't think it's obvious you can fail fast. I mean, the halting problem is hard to solve.
Well, it is.
I don't understand how you could ever guarantee to fail fast unless.
No, you can't guarantee it, but you can structure the solver in such a way that you will fail fast.
Yeah.
Okay. So the modern way that we structure solvers is a little bit better at that.
Right. Fair enough. Okay, so back to this. So I suppose I'm okay with this, so long as you change the examples and names, because they're really confusing to me, at least. Fine.
Yeah, so I agree that the examples are not as polished as they should be, and it's on my to-do list to clean them up before release.
Okay, fine. Okay, look, I think if we can change the variables, I think it'll be okay. I think it's understandable. Fine. Looks great. Should I look at anything else here right now? All kinds of wonderful stuff. What the heck is that creature?
That's a solution. That's a polynomial with lots of branches. So, right, each one of those lobes defines two branches of a solution. So you get 10 approximate solutions of that intersection point.
Wow. Okay, that's pretty cool. Okay, great. All right, let's go on. Integrate. Wow. Okay. A venerable function.
It's not there. I have examples, Stephen, because you'll drown in the examples in there.
Okay, what's new in this page?
Nothing. Go to.
I thought it said new reference page.
Yeah. Well, okay. That one is not ready. So.
Okay, fine.
But let's look at the. If you look at these projects.
That's weird. I don't know.
Well, it's probably because I'm not running in the prototype here.
Oh, okay. Yes.
I don't know why that's red.
It's because we haven't defuturized the documentation, so the build system doesn't know about it yet.
So this previously had no generated parameters, so to speak.
Right.
Correct.
Yeah, that's nice. Okay. So that's the main change, is generated parameters thing. Is that right?
Right. Yeah. So look at that second example where you have, you get not parameters, but parametric, new functions, free functions.
Yeah. Listen, this generated parameters thing, we have a whole circus of these things in these axiomatic theory, in the axiomatic theory repository thing, which we need to sort out. Oops, we just crashed.
What?
Okay, restart.
It's a new front end. Is that?
It is a new front end, yes.
Fresh.
Well, it is fresh, yeah. What do you think I can do there? Should I look at this this is probably opened in the, yeah.
That one has a bunch of graphics under it to summarize. That's probably what, I don't know if it's going to crash again or if, okay.
But you should report this because it's a good thing for John. Just
enable dynamics there, Stephen.
Okay. But you should, that is an ugly graphic.
I know. Still has the information. But yes, I agree. It's ugly. Really ugly.
So we're generating AppLF1s.
We avoid doing AppLF1s because AppLF1 numeric behavior is not adequate.
So what do we do instead of AppLF1?
We're not doing these problems, right?
So a lot of, there are a lot of ones where there are sort of larger, right? So you get like 3 hypergeometric functions instead of 1 AppLF1. So those you get that. And in fact, in some cases, you get much simpler solutions in AppLF1. And then those that really absolutely do require AppLF1, we return unevaluated for now.
What is the story with AppLF1? I mean, we've had that as a function for like 5 years or something now.
Devendra can speak to that, of what the problems were that we found.
The problem is that very simple examples can give an AppLF1 answer. So you're finding a volume of a solid, and it might give back a really bad answer in terms of AppLF1.
Yeah, I understand. But if you, okay, listen, there were two cases you described. There's the case where you need an AppLF1 and the case where you can get away without it.
Yes.
Okay, so what I'm caring about is the case where you, look, an AppLF1 is an exotic function. If you can get away without it, get away without it.
Yes.
But the question is, for integrals where the only way to give a result is using an AppLF1, what do we do?
We don't.
I
know. So I'm asking, what's the problem with the AppLF1 function?
That's what I asked Devendra to answer.
Right. So when you have an indefinite, so indefinite integrals are okay with AppLF1. If you have a definite integral, you need to work out branch cuts, you need to work out singularities, you need to work out the numerics.
So just give me an example of an integral that comes out. Isn't x to the x an integral that involves AppLF1?
No.
Oh, what's an example of an integral? Is it sine of x? It's one of the all-time favorites. Involves an AppLF1.
Oh. I mean,
do you know? I mean, Okay, so look, my main point is, what you're saying is we get an appel F1, it is a symbolic appel F1, we're still okay. Is that true?
Okay.
Okay.
So the problem is that, I mean, I can't tell you exactly off the top of my head since this was a couple of months ago, but I was able to construct relatively simple examples where, you substitute in machine precision answers and it returns unevaluated, right? And even though it may have been technically correct, so what exactly is going wrong inside of appel F1? That we don't know. I think that's a question for Sasha or Oleg or someone.
Okay, well, let's ask it. I mean, I have a question about appel F1 in general. I mean, so are there values where they're simply not known, or is it that we just don't have efficient algorithms for it?
I think that we didn't do a full job on appel. First of all, there are 5 of them. We only have 1. Okay, this F1 to F5. And so these are multivariate.
Appel was busy.
Well, yeah, but so generally speaking, multivariate special functions.
I know, are horrible.
Right. And we're going to start down that track seriously, but not right now. And so appel F1, I think they found enough sort of special cases that can be reduced to the functions we actually do have. But as tests now indicate, it wasn't adequate. It not complete coverage. And we don't know exactly what it is. It's its own investigation to trace that down.
But is there a defining series or something for this creature?
Yes, it's right there in front of you. I mean, on the appel F1 page, the sum with POC hammers in it.
Yeah, if you just open the details, probably it has it.
Yeah, okay, fine.
But I doubt that series is fully defining it. Does it globally define it?
Yes, it will define it, but the point would be that you have POC hammers over the denominator, etc. So there'll be lots of exceptional cases.
Yeah.
But straight away.
You mean, I'm sorry, you're saying that there are things that blow up because there are POC hammers where there are integers which give you denominator zeros and so on. Is that correct?
Right. And so you could have, let's say you might have a relation between the numerator POC hammers and denominator POC hammers, and they might miraculously cancel the singularities, or they may not. So it's the same story with hypergeometric 1F1 and things like that, but much worse. And just to answer your earlier question, if you go down to the property relation on the same page, you will see an example of the integrals which you're talking about earlier on. So typically you have an abstract power of some polynomial like x plus 1 raised to n, and that will lead to an appel F1. But it's really hard to figure out when they should be given and when not.
Well, I don't understand. Why are you saying that? When they should be given as in when there's an alternative to an appel F1 or what?
Well, the thing is that the new functionality sits on top of the old one. And for efficiency, we call it before the legacy integrate. And there's no way for us to figure out in advance that, we have...
Okay, so in other words, it's giving, the new functionality is giving back an appel F1.
Yes.
But the older functionality might give back a sum of 3 hypergeometric functions or something.
Or it might even give back an elementary answer because those hypergeometrics might simplify to...
I get it. But so I don't understand why the algorithm isn't, you run the new stuff, it gives an appel F1, you say, okay, let's put it on the shelf.
Yes.
Let's keep going and see whether the old stuff gives something great.
Yes.
If the old stuff fails and says, I can't integrate it at all, pick the appel F1 back off the shelf and return it.
Yes. Now, if integrate were a very modern function like sum, which was written in 2007, we could do that. The current integrate is horribly recursive. We don't know how often it will try something.
Okay, well, whatever. That sounds like that's a different explanation, okay? That's a different thing. What I thought you were saying is that something is wrong with returning the appel F1 because of the...
That was the argument given, Stephen, okay? The reason we avoided, right now, the new rules, Ruby means rule-based integration, okay?
Yeah.
Okay, so the new rules, we excluded the rules that do emit appel F1s. Initially, we had them with them.
I see.
We've now excluded them.
Yes, and we lost around 400 examples, but I think that's better to hold off until we have a better understanding of integrate. It's the first time you kind of poked into
Okay, but hold on.
And Stephen, if I may, I just want to say the reason we turned them off is because I went through all of the examples on ref/integrate, and some of these elementary examples were returning things that were no longer, once you substituted in numerical values, didn't work, and that was worse than returning it for abstract things that we can't currently do.
So you're saying it's better to return an unevaluated integrate that you can evaluate numerically than to return an AppLF1 that blows up when you try and evaluate it numerically.
Yes,
Is that the basic claim?
Yes.
Okay. I mean, okay. So let me just ask you, with respect to AppLF1, what should be involved in? I mean, I don't quite understand. Is this something where, for example, the coming attraction of function evaluation is surely machine learning stuff, where we basically, just like, 30 years ago, we started using these economized rational approximations that other people hadn't used for function evaluation. I think the coming attraction is using, neural net type stuff for that. And I don't know.
I doubt that, Stephen.
Why?
I don't know how you get, there's a lot of technology that needs to be developed to control the precision in that. It's not like data science. It needs to have, needs to be correct.
Sure. But I mean, the question is, what the obvious thing to try to do is to try to learn one of these things. And then
we could try that, but I just very much doubt that that's going to work. Very much. Because all the machine learning stuff is built for something that's super approximate. It's super good at dealing with very fuzzy and things and still be able to get a quantitative.
No, you're right. The idea of having a high precision answer is a bizarre for modern machine learning.
Exactly.
And machine learning is about reducing a large number of things to a small number of things, whereas here there really isn't a natural way to.
Well, it depends how exotic the function is. I mean, look, what it might be useful for is getting initial approximations if there's a way to tighten the approximations up.
If there is.
Right. Okay.
Right. Although to train it, we would first need to know what they should evaluate to.
Sure. Does anybody know? Are there tables of AppLF1 that anybody ever computed? Or is it kind of, wild?
I have not seen that much literature on AppLF1 at all. And I think that, to be honest, once we finish this current Hoin project, we'll go on to AppLF1. That would be the plan, actually.
What is the genealogy of Hoin versus AppLF1?
Well, the point
Hoin is univariate, and it's sort of the next level of number of singularities beyond hypergeometrics and Meyers and so on.
I see.
So that sort of pretty much covers the second order
differential equations, ODEs.
Yes.
ODEs, yes.
So what is the AppLF1? Is it a solution of an ODE?
No, PD.
So there are two variables. So
yeah, right. But what kind of PDE? Is it linear PDE or what?
They're linear systems, if I remember it right.
Yes.
Work done by.
Most of them are linear PDEs or systems of PDEs. Like the Horn system is one very classic case of system of hypergeometric PDEs.
Okay. All right. Let's go on. Cool. So. Okay, same constants of integration deal. What is this? I should be able to sing this in the other one, but let me not worry about that. Okay, so what are we seeing here? So this has got another.
This is improvements to DSolve. Okay.
Yes.
And there are two projects effectively. One is that currently DSolve often spends an inordinate amount of time trying to evaluate an integral. And often fails too.
Yeah, I get the idea. So you're just reducing, you're unraveling the ODEs into something which just has integrals.
Correct.
Well, typically you get back one good solution like e to the power x in the example over there. The other solution is impossible to compute basically. So we decide when to give up and then don't return it.
No, I understand. I understand. So the issue is, so right now you've got method inactive integrals, which
But that's automatic, Stephen. It's
It'll become
right.
automatic. Yeah. It was just need to be tested. Now it's tested and it all looks good.
Yeah.
So wait a second. So you're saying you can predict when the integral you generate will not actually be evaluable?
Yes. And the reason is this, that if you look at the output, it's essentially an indefinite integral, nothing more. It's 1 to x. So we try indefinite integration from integrate. If that fails, we give up. And the worst that could happen is that someone wants the integral to evaluate. They just do an activate and they can get that to go on forever.
Ugh.
So
Wait a minute. So you are returning, I mean, this is the first time we've ever returned explicitly inactivated things.
no, we have a desolve for PDs.
PD solutions return also inactive sums.
Right. And Meyer-G reduce returns inactivated things.
Nobody will ever figure out what to do here. Unless we have some visual indication and some mouse over, nobody is ever going to figure out. They're going to say, what do I do with that integral? I want to, I mean, in other words, if I fill in, let's say the integral has a bunch of symbolic parameters and it can't be evaluated symbolically given those arbitrary symbolic parameters. But if they were to go in and specify those things, then it could evaluate. Am I making sense?
Yes.
So, but that won't work if the thing is actually explicitly inactivated.
Right.
You need to activate them, and we show that. We will show that with examples.
I don't care. People are not going to figure it out.
What do you mean? If you that first one is not inactivated, which is the point. If you hover over the second one, there's a tooltip telling you it's an inactive integral.
Okay, that helps. I don't particularly like that tooltip, but it helps that it says that. People are not going to figure out. I mean, we should expand that tooltip to say something clearer and better.
I think we could.
But so my question is, when we do this, gosh, this is a mess. This is complicated.
No, it's not a mess.
Well, it's complicated.
Well,
Because if you substitute into this, okay?
if you substitute that solution in, it will actually do the right thing. If you take derivative of that, it will work.
Right, I understand. If you take a parametric derivative of that thing, it will work.
Yes.
But if you expect the thing, if you substitute x equals 3 there or something, it definitely won't work. Or substitute, let's imagine I even substitute x equals 1, where that integral will actually be 0. Right, it's definitely not going to do that correctly because it's inactivated.
You need to activate it, yeah.
No, I understand. So what I'm saying is, when you substitute in there, people might have thought if it was just an ordinary integrate that was unevaluated, see what I'm saying? Then, I mean, like for example, if I do an integral here, if I say, I don't know how to do this and have it, sine of x, comma x, okay, that will be unevaluated. Actually, if I say sine of x, xab here, or actually, let me be more accurate, x0b, right, that will be unevaluated. If I say that, arrow b, arrow pi, right, that will evaluate,
Yes.
right? But nothing like this will work for these inactivated integrals.
Right.
Okay, so that's the point.
But you will get back an inactive integral. You'll see it. Sure, I'm saying.
Yeah, I understand, but you won't know why that happened, so to speak. I mean, so what you'll see then, if I do this, if I say inactivate, okay, great. I have an inactivated integral. It's nice that this is, now why aren't these in lighter colors when they're inactivated?
Because they're not inactivated. Only the integral is inactivated. So really, you should have put a comma.
Oh, I see.
Integrate.
Actually, this helps me because this is, okay, so I don't even know why the whole expression is mouse over it, which is, although it's good, but I see that integral sign there is brown.
Yes.
which is good. So this is really inactivated. Is that right?
Inactive.
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 Yeah.
Active. Of the integrate, yes. Exactly.
Okay. So now if I say there, obviously B arrow pi, oops.
No, that's still not going to.
Yeah, obviously it's not going to work.
Yes.
Yeah. Look, I think we should improve that tooltip and say something more useful.
I think so too.
Like what? I mean, that would be extremely non-standard.
Well, but just needs to say use activate. Right.
But like I said, that's extremely non-standard, and we
For what? Non-standard for what?
for tooltips in general, and we have a bunch of right. Every inactivated thing has a tooltip, which is just inactive of the thing.
I know, but maybe we should improve all of them. I mean, I'm not sure what they should all have an instruction set, instructions with them. But I just think that thing is very, it's very austere to just say that. I think we should look at a design that, let's look at some examples of inactivated things and let's try and come up with a plusher design for that tooltip. I mean, right now it isn't designed. It's just a plain text tooltip. All right.
So you see, then we get a huge performance improvement, like a factor of 2 with just this small change.
Well, I'm sure we do, I'm sure we do because we're doing less.
Yeah,
right?
but we're doing the wrong. We're making effort in the wrong place, where we had no hope of getting the answer.
No, I get it. I mean, I get it. You're saying, but are there integrals where you would try, and if you put the effort in, you would succeed, or are these integrals where up front it's impossible?
I know upfront because, I mean, frankly, I've got years of experience in looking at these, and I know that there's a zero chance of evaluating an integral with, so to speak, definite integral methods when it's already failed indefinite integral mechanism. Now, if it's piecewise, we'd allow it to go through. So there are cases where we'll judiciously allow it to go through, but typically it never helps to try and evaluate an integral beyond a point. And you get like an answer in a fraction of a second versus an R.
Yeah. I'm going to have to leave in a moment here, but let me just scan ahead for this. I would like to come back to this. I feel like this requires a bit more discussion. This, returning inactivated things.
Sure.
I think.
Could you just scan through the rest of it? So
yeah, let's just take a look. What else?
look at that benchmark. I think that has. So part of what we've been doing, we haven't been going back to this part of desolve. This is both of these things, the inactive integrals and systematically working through.
So, wait a minute. I'm sorry. When you say unevaluated, you're saying that if you leave them if you allow inactive integrals and you consider that a solution, and you consider that a solution, then this is rather ugly. I don't know what happened to this magnification, but mean leaf counts. Okay, cool. Yeah, but I mean, okay. You're saying you now count as a success.
Yes, exactly.
Okay, fine.
Yep.
So you changed a little bit.
We changed the game a little bit. Yeah.
Yeah, right. So this is now a completely different thing here. This is
reduce. Okay. So these are recognizing dependent structure or independent structure to get a big performance gain.
And what's the
this is
meta?
just under the hood.
Yeah, okay. Well, that's wonderful. But what's the meta method for? I mean, like there could be 6,000 different kinds of structures that you could look for.
Yeah.
How are you actually looking for them?
Well, this depends what's called. So if you have an equation, often when you have big equations, they don't all involve all variables. They involve some.
Sure.
And you can structure them. If you're very lucky, you actually have sort of two independent systems of equations, and you should solve them independently, because the algorithmic complexity is more than linear. So if you can split it to solve two smaller problems, you've had a big gain. And in this case, the worst case complexity is exponential or doubly exponential. So it's a huge gain.
Mm-hmm.
The other way you can do it is if you have what's called block triangular structure.
Sure.
Which means that there's some equations that, let's say, it only depends on YZ, and one that depends on XYZ. If you solve those fewer variables first, then you substitute back, and you have, again, smaller problems to solve.
All right, but anyway, the basic bottom line is whatever it is that we're doing for structure probing, it's going to scale okay. We're not going to get something where there are, where we've got one structure to probe.
No, this is super fast. It's in below a millisecond.
Good. Okay, let me just have a very, very, very quick look here. Oops, let me look at this. Do I have to look at this in the prototype branch?
Yes.
Yeah.
Oh, Splatosaur. Well, it died. So
Would you like me?
If you close the graphics sections, I think it would open correctly. I think it's the graphics I'm guessing it's the graphics that's problematic in the new front end. And there's another one that had also, I don't know what graphics is problematic, but closed.
Jose, there's a general bug with, not quite correct non-canonical graphics crashing the front end. So that may be...
Wonderful.
Yeah. Would you like me to share? I don't have that notebook handy, but I can certainly illustrate those two functions.
Okay, super quickly, because I've got to run off here.
Okay.
Oh yeah, I got to run too. I'm in deep trouble.
Okay. Low zoom. Okay, so prototype. So the new C type setting you've already seen. It's using,
I agree with it.
and it has a little tooltip to let you know.
What does the tooltip say?
It just says C, so you know that this is capital C and not some strange character. And then traditional.
Maybe it should say C of 1. Maybe the tooltip should have the whole thing. I think that would be clearer, especially given that the
right. We can, we can do that.
Okay. Right. Okay. Next.
And then the other thing.
Numbers.
Right. So if I do root down to the 7th.
Well, that's exciting. What I'm seeing on your screen with screen tourism, that vector less is cool.
That's for the optimization side.
Yeah. Ampersand. And I hope I typed this in correct.
Try another polynomial.
No, slightly more complicated. Give me some constant here.
Right. Yes, I forgot the +1. There we go. So in the past, you would get basically something that looked like what I just typed in. Now you get a little icon telling you.
I don't especially like I like the concept here. Mm-hmm. I don't like the particular form because it looks to me like it's square root of minus 0.797.
I see.
See what I'm saying? I don't think that quite works.
It's an indication that it's a root object.
Well, maybe it should come after. Maybe the root thing should come after the number.
Fine.
It just doesn't look right to have that square root thing. Or there's got to be some other way of doing it. This isn't quite right. Because otherwise it just looks way too much like square root of that thing.
Okay.
All right, listen, I have to run.
What do we do from here on out?
Let's schedule another one of these. Probably it can be done in half an hour. Maybe we can combine it with something else. But let's actually not count on that. Let's get a full hour, and let's also have availability of some design folk to look at some of these things like plusher, inactivated tooltips and so on.
Okay.
Okay, and then we should be able to nail it.
Is that automatically scheduled, or should we request it?
I think you have to request it.
Talk to you then.
Okay. All right.
Thanks, Stephen.
End of the live stream. Thanks, guys. See you later.
Bye.
Bye.